Okay, I plan to have a full section on climate modeling from a book that is a brief focus on climate modeling. But in this book that we are using for climate science, there is a chapter on climate models. So I will go through it, and you can get plenty of information from here as well. And if you're interested in more details, you can go to the third section when I post that. So let's start with weather forecast modeling that we already kind of mentioned a couple of times, where we said weather forecasting is an initial value problem. That means typically the ocean is prescribed in some ways because it varies very slowly compared to land and atmosphere. So let's say the sea surface temperatures are prescribed, and the integration or forecasts are typically made for short range, which is 1 to 3 days, medium range, which is 3 to 10 days, and most of the places don't have right now any predictability beyond that. And the atmospheric model and land model are initialized at every point with some basic variables like temperature, humidity, forcing is given of course from the sun, land use types, various other factors get prescribed, and some things are prognosticated or forecasted like temperature, precipitation, winds, humidity, etc. So that initial value problem, we said before that it gets chaotic after a few days. Small errors in initial conditions become large errors in forecasts, and there are techniques like data assimilation which are used to initialize the model, and every 6 hours you may start the forecast again with the new initial conditions, and so on and so forth. So here is a schematic of it. So there is the globe. You are looking at variables in the atmosphere, so differences in the vertical layers. Typical variables are temperature, wind, clouds, humidity, and precipitation. And there are exchanges of momentum, energy, mass, water vapor, and so on. So the entire globe is discretized into boxes like this, and a computer model is built to numerically solve the equations of motion, which I will show in the next slide. Because they are very nonlinear, we cannot have a analytical solution for them. We cannot just integrate them by hand, so we need computers to discretize the globe into these grids, as we call them, horizontal and vertical grids, and ocean is prescribed, as we said. So variables at the surface include temperature, humidity, air pressure, and so on. Okay, so this is a weather forecast model. The equations involved look like this for both the ocean and the atmosphere, and land has some equations. So we have Newton's second law, F equal ma. So you have the momentum equations. So this is MA, and that's the forcing that is in some ways prescribed. We won't go into the details. So this is the x direction or longitudinal direction. Because we are on a sphere, you can see the coordinate system. It has latitudes and longitudes. So this is the meridional or latitudinal direction. This is the vertical direction. This is the mass continuity, so how mass is being conserved, and there is thermodynamics, of course, which tracks how temperature is changing with solar forcing, humidity, and other things. Okay, so obviously this is an introduction, so we're not going to go into more details, but if you want the details of these equations, you can look up my ocean atmosphere dynamics course, or dynamics of tropical atmosphere and oceans, which have the full equations and lots of discussions and details as well. So how do we go from weather model to climate model? Weather models are almost always explicitly for forecast or understanding forecast processes, weather forecast processes, so that we can improve the weather forecasts, skill, etc. Or we have a range of models that take us to lower frequency processes. So beyond a few days, at some point we said sub-seasonal to seasonal time scale. So at some point we transition from weather into climate. They are not truly independent, right? The diurnal cycle of radiation affects the seasonal cycle. The seasonal cycle affects the year-to-year variability, and so on and so forth. So models can have various level of complexity or level of detail, and they can have various levels of comprehensiveness or the number of components. It absolutely depends on what your purpose is. So if you're just trying to understand something like the zonal mean meridional energy transport, you would do something like energy balance model. So you would take total energy being received, total energy being emitted to space, and you may do a diffusive model or some sort of an energy budget. You also have box models where instead of numerically integrating equations like these on a computer, you would just assume that an ocean or the tropics are a box. Tropical ocean is a box, tropical atmosphere is a box, land is a box, and then you exchange things between them. That reduces to simple equations, which can teach you a lot, which we will see more in the third section of the course if you're interested. And then we transition to what are called Earth system models, or and they themselves have various levels of complexity. We kind of mentioned what an Earth system is. It's where we begin to add not just physical climate, temperature, winds, precipitation, clouds, etc., but we begin to add chemistry, carbon and other chemistry in the atmosphere, pollution, etc., and often we also include somehow human influence or human activities and feedbacks between vegetation and climate, and carbon and vegetation, carbon and climate, and so on. So the Earth system models themselves can be very comprehensive. So up here the comprehensiveness and complexity goes up in Earth system models. We will see a schematic of that. But at the lower end, transitioning from box models, you have what are called Earth system models of intermediate complexity, where various simplifications are done in the representation or the complexity or the level of detail, and you sacrifice the comprehensiveness of the processes that you are modeling. So they are often used for long simulations because these tend to be simpler to run, need much less computational power than these, for example. So they can be integrated for a long time to understand processes at, let's say, paleoclimate timescales, Holocene, Ice Age, and so on and so forth. As for climate models, they have various components run separately or together. So you can have a ocean general circulation model. So a general circulation model is something that solves these equations, this set of equations in some form or the other. You have atmospheric GCM, where the ocean is just giving some energy to the atmosphere, and only the atmosphere is being integrated, whereas in the ocean general circulation model, atmosphere is forcing the ocean with winds and heat fluxes, fresh water and evaporation, and ocean circulation is the focus. Atmosphere ocean general circulation models are where the ocean and the atmosphere talk to each other. So things like El Nino, which are very much a coupled phenomena, monsoon, which is very much a coupled phenomenon, and so on, are done with these, and also climate predictions, which are seasonal to interannual time scales. Okay, and of course system models, which have the full complexity, chemistry, often some sort of dynamic vegetation, and so on and so forth. Okay, so here is a schematic for a global atmospheric model. You find many such schematics online if you wish. So let's start with this one here. We are looking at how the atmosphere is split into grids, because those equations that we looked at cannot be solved by hand. So we discretize them by splitting the atmosphere into many boxes in the vertical and in the horizontal. There are issues to deal with, like the pole is singularity, so you have to move it around, you have to do lots of things. But without getting into those kinds of details, you have latitudinal and longitudinal horizontal grids, so x and y directions, let's say, vertical grids, so height and or pressure, and then you are solving for these kinds of equations where the ocean is exchanging energy, precipitation, water vapor, there is a water cycle in the atmosphere, you are taking solar radiation at the top and you are creating on the sphere, you are creating a region of surplus energy, region of deficit energy, and then you are trying to produce the circulation in the atmosphere. You can include various levels of details on land. Chemistry may be prescribed, land cover, distribution of vegetation. You can hear the chopper. Can hear the chopper going by there. So we'll come back to this figure again, which is the Earth system that we looked at before. So between the grids there are exchanges of information, mass, water vapor, heat, and so on and so forth. Okay, so let me stop this introductory podcast here, and then we'll add details as we go along, but you get a sense of what the models are all about and what various levels of assumptions involved would be. But we will add more details to show that even though we showed some equations, there are no equations for some of the processes, or we don't have enough knowledge yet to write fundamental theoretical equations for some of the processes, and they are represented by statistical empirical relations based on observations, which are called parameterizations. So we will see what that means when we come back. Okay.